Aubrey.
Yes.
Happy Thursday. Good morning.
Good afternoon, Michael. What have you got for us today? What's on the kitchen counter?
Well, let me tell you what's on the kitchen counter today, Aubrey. It's the
Okay.
final episode of our mini-series. So
It
I
is.
thought we'd go big with this one. So my question for you is, if you could send anything to space, what would it be?
Okay, that's interesting. Well, I don't know. I mean, maybe a piece of technology like a phone or something just to, I know that we've put out random things in the past in our history. What about you?
I'm quite a sentimental person, so I think something like I like the idea of putting like a family photo, like something that will go onto like a spaceship that will just sail into the distance forever.
Yeah.
I quite like the sentimentality of that. Like the Voyager probes have got those gold discs in them.
Yeah. And I assume, obviously, we're going to be talking about space today, right? In this episode.
Well, not us personally, Aubrey, unfortunately. That would be quite cool. But we are going to be looking at computing in space on the moon and beyond.
Nice.
So I'm Michael Bird.
I'm Aubrey Lovell, and welcome to Technology Now from HPE.
So, Aubrey, as we said in the introduction, this is our final installment in our History of HPE in 10 Objects miniseries. And this time we are exploring, new frontiers.
Ooh, very exciting. And like the other episodes, this is, of course, a video episode in case you haven't noticed. So make sure to check us out, not just where you listen to podcasts, but also where you watch them too, so you can see the objects we are actually talking about today. So, Michael, with that said, I have a sneaking suspicion about what today's topic might be.
Yeah, man. What's your suspicion?
Okay, it's not far of a stretch here. We talked about sending things to space, and I know that we've done episodes in the past about sending supercomputers to space, which I would say is a pretty big deal, right? So can we possibly be talking about supercomputers in space again?
Yeah, nailed it. You're absolutely right, Aubrey. Because in the final episode of the miniseries, we're going to be exploring new frontiers and the Spaceborne computer program, which has already sent a few supercomputers into orbit already, and we'll be sending them even further in the near future.
Very exciting. I think this is one of our most fascinating topics. So what are the final three objects we'll be looking at today?
All right, so the final three objects are the Spaceborne Computer 1, the Spaceborne Computer 2, and, drumroll please,
That was my poor version of a drum roll.
We should work on our drum roll. Anyway, the final object is Spaceborne Lunar. Third object, Spaceborne Lunar.
Nice.
Yeah. So I think we should just go straight into my chat with Norm Follett, the Senior Director, HPE Global Technical Marketing, Space Technologies and Solutions, who told me all about the why, the what, and the how of the Spaceborne computer program. So, Norm, thank you so much for joining us on Technology Now. We have such a cool selection of objects for this episode.
Yeah, fun.
But let's start with this one that we're stood in between.
Well, this is Spaceborne 1. This is the chassis for Spaceborne 1. This is the device that started it all. I would say in HPE history, this is perhaps as interesting or as impactful as the oscillator or HPE scientific calculator in the impact and with respect to the innovation and breakthroughs that it facilitated.
Why is this object in particular so important to HPE's story?
I think it's beyond the HPE story. I think it's a story of, humanity exploring into space. So NASA, over the years, as they started to develop spacecraft and started to develop compute systems, they would build their own computers, proprietary computers, and they would spend tremendous amounts of money on it, tremendous amounts of time. And what really happened as part of the commercialization of space, NASA had that initiative in mind to use more commercial products, get private companies involved, get companies that had expertise in areas such as computer science directly involved in what they were doing.
Can you sort of tell us the story of how this got to being up in space?
Its initial mission was 1 year in space, and it was only a test. This is only a test. And what they did is they had a duplicate system in Chippewa Falls, and they were running high-performance compute benchmarking tests. And NASA wanted to see if there was any delta, any performance change between that. And there wasn't. It did so well that after a year, NASA asked us to stay on station. And so we spent an additional 6 months in orbit, picking up operational tasks. So they immediately, kind of the light went off and they said, well, while you guys are up there, can you actually do some work for us? So we went from a test system to a production system.
Wow. So this chassis is sort of standard size and shape for the International Space Station, but it's not a standard size and shape for traditional computing.
No, it's not. So whereas like in your data center, it slides out.
Sort of
This
have
is slid in. This is slid in sideways. So that was kind of the first bit, was really getting in there. And when we talk about hardening, physical hardening, right? Survive the shake, rattle, and roll. But it's also a software hardening. Now, that I mentioned that philosophy that NASA had about can't fail, can't fail, can't fail. One of the philosophies that Mark and team brought forward was, well, it can fail because things do fail, but it recovers gracefully with no data loss. And so it's a software hardening process. So physical hardware hardening, and then a software discipline and an approach applied to the systems inside. And that's what made this system successful. And also, I think, as most space enthusiasts realize, the problem across the board always with any mission is power and cooling, right? So the first job from a power perspective was to take 28-volt DC that the ISS generates, solar power, and then convert it. Now, what you don't see on this configuration is that the power converters actually were provided by NASA. They had some on station. Dare I say they were handy. And so the power converters actually strap onto this box, right? And so there's a cable coming into the power converter. This connects to the power converter, and then it goes in and it went into some traditional power supplies that you would find in your data center.
The servers inside of here, they're off the shelf.
Correct. Now, this was meant for no maintenance, no astronaut intervention whatsoever. It either worked or it didn't. And when it went down, it was going to be down. It never went down. Year and a half, it never went down. So this is a definition of a black box, although it's white.
Yeah. So this was in space. Presumably there isn't a very, very long Cat5 cable going from the International Space Station down to Earth. Are we sending tons and tons of data down to Earth?
Well, this is the ROI of what we're really doing here. So we operate, there's a small command window. We operate, once a week. Candidly, we get a command window where we can talk and interact with it. We often stage up software and execute it and kind of batch processing and do all that type of stuff. But what this addressed, and this is where the light went off for NASA, this is the classic edge compute solution. And what I mean by that, do the computational work at the point of data acquisition and send back the answer.
Right. So
send back kilobytes rather than gigabytes of data.
So rather than if you had a module that was taking photos, rather than send every single photo down, maybe analyze those photos and then just say yes or no to something, that sort of thing. Yeah,
that's actually a good prompt for one of the solutions that we actually developed. But I will say that that Spaceborne 1 also won the very distinguished NASA Technology Achievement Award.
Wow.
And that's, very few of those are handed out. That's how excited they were about what we were able to prove and do.
This sort of drove that edge computing, like the necessity of edge computing, just due to that data connection.
Well, it reinforced it. And it reinforced that this is a really good thing. And again, originally it was the task was to be up there for a year. And why? They were preparing for deeper space missions, right? Mars. And they figured, well, we need a system that's going to last a year. Can a commercial off-the-shelf system do that? They did not have the intention of having an edge system, high-performance compute on the space station until they realized its value once it was in place.
This is Spaceborne 2. We're going to come on to this gold thing in a second. But so just describe what we're looking at here and maybe compare it to Spaceborne 1.
Okay, so a couple of things. So this chassis is designed to be serviceable, right? So that's the biggest thing. You can't get those doors open, but here...
So it's like these little panels here to open it.
You can actually get that open, right? And so, again, it's also turned to where the pizza box one-use servers are turned sideways, so kind of a non-traditional installation. But again, it's designed for astronauts to interact with, and I'll talk about that in a moment. But a couple of deltas you'll notice right away. So these are fuses, very traditional fuses, input, output, the liquid cooling, and then these are the power connectors. Now, remember all those plugs on the other unit? Yeah. These are the two power connectors. What's interesting here is that we actually have, I described we had a power converter outside Spaceborne 1. The power converter is inside this chassis. Right. We found a 48-volt DC power supply, but the station produces 28 volts. So the power converter in here jacks the power up to be compliant with these systems. Yeah. So the delta here is we moved it inside. We're dealing with it ourselves. Less setup for the astronauts. That's another part of the mix, right? They don't have to deal with any of that as well. And I just want to say both Spaceborne 1, Spaceborne 2, we're not involved in the avionics of the ship. What we are is a scientific platform. We're a scientific platform for the international scientific community to do work on the station, to do high-performance edge computing on the station. And we've enabled a wonderful series of experiments. You mentioned just that simple thing about photos, right? And so that's an inference engine, right, if you will. Astronauts on the space station, they actually have what they call an EVA season, and that's spacewalks. And that has our friend here, Major Tom, our friend right here, Major Tom. That means that there's certain times of the year where there's less radiation outside ship. So they schedule their tasks and they do all that type of thing, a little less risky. But the things that wear out are gloves, because that's the touch point. Just like you working in your yard, your gloves wear out. So what they would do is they come in from the spacewalk and they take literally hundreds of photos of an individual glove. And then they stream or send those photos down to a shop down here at Johnson, not far from where we are today. They look at those pictures and they go, oh, this one looks a little worn, and they circle it and they communicate back to the astronaut. Look at left hand glove number 14, and we think there's a wear on index finger leg. And what they have to do is they go through a certification process to certify that that glove can go back out. It takes a lot of effort.
We talked about how slow the connection was going back to Earth.
Slow the connection, and then you have to have eyes. Humans looking at communicating back and forth. Takes weeks to recertify a set of gloves. So as such, they carry all kinds of gloves. They have extra gloves. What we ended up doing was building an inference engine, a machine learning engine, and running it on Spaceborne, took all those photos in seconds. We go, look at glove 13, index finger, right? And so it just eliminated all that processing. Now, today, NASA does both because they're still proofing that system. They came back and they said, they gave us the NASA Team Flight Award. So another award, just say, that's amazing, because they're thinking, what are we going to do on the moon? Now we can scan our equipment and we can say you're good to go or you're not. Changes the numbers of backup equipment that you need to have, but also it just changes the timing, right? And so it keeps everybody productive. So that's just one example. So many great examples of us doing breakthrough science, not just to enable what our astronauts are able to do, but for, improve our conditions here on Earth as well. One of the things that we like to say, proven in space, available on Earth. So meaning that if we have the ingenuity and the wherewithal to solve some of the toughest challenges, in space, in some of the harshest environments, we can help you in your data center. Secondarily, moving along the human condition, right? Because we're able to do science and help the scientific community learn things that they were not able to do and are not able to do on Earth. There's a new market opportunity, right? Edge computing on the moon, in orbit, on Mars, it's going to be a necessity for human survival. And there is a legitimate business case out there.
The key thing, I guess, is that you're not having to send data back down to Earth or every single piece of data that you're capturing. You can plug it into this computer that's sat next to you on the International Space Station, run the experiment on this, rather than having to send it back down to Earth. That's what's saving time, right?
Yeah, absolutely. And having a high-performance compute platform that can actually handle some of that experimentation. Yeah, okay. And that also included something called a federated learning model. And the federated learning model, for people that are familiar with it, it's really about having large data sets distributed and everybody doing work in that distribution and then sharing the result with each other. And it becomes a model that's shared. So you're not having to move large data sets to synchronize with everybody, but you have the opportunity to work with those large data sets because you're sharing the resulting model. And again, NASA very, very excited about that, because what that means is that as they explore other planetary bodies further out in our solar system that we can learn as we go and continuously share information and again, create self-reliance.
So for Spaceborne 1, Spaceborne 2, we'll come on to that in a second. Will there be a Spaceborne 3?
Well, actually, there really is a Spaceborne 3. We did a reflight. We upgraded the internals to one of the lockers. That's really the third iteration. So on January 30th, 2024, we launched from Kennedy Space Center.
Do we have a fourth one then?
We do indeed. Would you like to hear about it?
I'd love to hear about it.
We have an opportunity working with a partner to go with them on their first rover that they're bringing to the moon. And that mission is called Griffin 1. And Griffin 1 flies to the moon, lands on the moon. The rover climbs off. That rover's called Flip. Climbs off the back of that lander, starts to explore the moon, uses our Spaceborne Blade computer to actually map, monitor, and gather intelligence on the surface of the moon and conduct the first AI experimentation on the surface.
So this is Spaceborne 4?
This is Spaceborne 4. Spaceborne 4 for Flip.
So it's about the size of a graphics card, I think.
Yeah, it is. It's less than a foot long.
How is this able to do what this is able to do?
Well, it doesn't really, right? And what I mean by that is that we have a different challenge. With Spaceborne 2, we flew the largest amount of memory to ever go to space with our partners Kioxia. That was 120 terabytes of space. This little fella, also we're working with Kioxia, has 1 terabyte. Okay, so there's only so much you can do. Now, what we did differently, because this is the fundamental difference. These guys, as I described earlier, we are existing in an atmosphere. Now, atmosphere is the internal spaceship, the International Space Station, and same thing the astronauts breathe. So we exist in an atmosphere. Here we are operating in the vacuum of space. Very different, right? Lots of different challenges. So what this chassis that we've designed is actually, it is the cooling system. So we actually have a series of techniques inside that actually allow this chassis to heat up, right? And then it heats up and it's bolted to the convection plate on the rover, and it's designed to transmit or let the heat pass from the chassis to that cooling plate, and then let the Flip radiator system take away the heat. And this will be the most highest performing computer to ever be on the surface of the moon when it's there. But we're going to quickly surpass that, because we plan to bring our EL product line up to the surface of the moon on the larger rover, where we have more space to work with. And we also have the notion of building, ideally, what Astrolab calls as power towers. So think of distributed edge computers creating a mesh network that will also be delivering what we're doing with 5G networking as well. The ISS was a preparation for us to go further in space, and that next further destination is the moon. The moon is preparation for us to go further in space, and that next destination is Mars.
Wow. Okay. Before we come on to Mars, because I do want to talk about that, what purpose is this computer? What's its purpose on the moon?
Well, we're going to do a couple of different things. So I mentioned the federated learning model. We want to show that you can have a multi-node federated learning model. Now, what's really cool is the 3 nodes will be Earth, probably Chippewa Falls from our lab there. We'll have the ISS, and we'll have the moon by the south pole of the moon, and they will be sharing data sets and information as this rover drives the surface of the moon. And we're also going to be doing a LiDAR mapping exercise because despite, we have great photos of the moon. It's been, we've had photography for decades now over the top of it, but it's very different when you get on the surface. There's a lot of information to learn. So this will be running that. We're going to be driving around mapping the surface of the moon, and this computer will facilitate that.
What sort of connectivity does the Spaceborne Lunar have? I feel like the ISS is slightly more obvious. It's going around the planet.
Right.
It's probably got direct contact at various points.
Right.
How on earth does this speak to planet Earth?
Well, how in moon does it speak to planet Earth? So a couple of different things. Again, it's a symbiotic relationship with the Flip rover. So we're dependent upon the Flip rover subsystems. They have 2 different satellites that they're going to be working with, one in Australia, one in Europe. So we're going to try to keep kind of that continuous dish of communication. The pipe is very narrow as far as the connectivity back and forth, what we want to do. And it's a shared experience. So in fact, some of the things that we're going to be doing, just as we do with the ISS, is that we queue up the resulting data sets, and then we get our command window to communicate that information back and forth. The number one export for the first 10 years that we're going to be on the surface of the moon is data. The number one export is going to be data. And we're in a position to help, mine that data and make that happen. And just to put things in context, when you think about the volume of the moon is actually the size of Africa, right? So you need some wheels to scoot around and explore that. And you need the ability to analyze, measure, and learn from that exploration. And that is what we hope to do with our continuous Spaceborne program, bringing edge computing to some of the most diverse and challenging environments.
What's the next step after Spaceborne Lunar?
Right, we have the notion of a Spaceborne 5, and that is going back to the ISS. In the industry, you'll hear a lot of conversations and talks about orbital data centers. People, saying, hey, you get power for free, sort of. That you get cooling for free, well, sort of, or it's going to be less expensive. I would contend that we actually probably do already have the first data center in orbit with what we've been doing with Spaceborne 2 and the Spaceborne program in general. But we plan to expand that. We plan to bring Gen 12 servers up there and give even more compute capability. We may go larger than 2 cabinets. We may build, 4 cabinets, 6 cabinets, whatever. We'll just see, where that leads us. And then, of course, our partnership with Astrolab, they are not just focused on the surface of the moon. They're building rovers and equipment targeting other planetary bodies, aka Mars. A couple of different things just very quickly there. They're also part of the Artemis program. And we have a relationship with them to be part of the Artemis program. That's a return to the moon. And that's where we plan to bring, probably some more, expanded system bigger than this in one of our new EL 8000 product line. Potentially, we're working through that with the product teams now and the BU teams. And so that's where part of our relationship extends. And then also Astrolab is competing for the Lunar Terrain Vehicle contract directly with NASA. And that means that if they win, and we believe that they are a top candidate to do that, and that's going to be announced in November of this year. It's been a long process, but that will result in a fleet of rovers. So we have the potential to have a fleet of spaceborne computers roaming, exploring, and learning about the surface of the moon. And, it's an honor for me to, just even have a little part of it.
Thank you so much, Norm.
I think that was a wonderful conversation. I really love just learning about all the latest and greatest of what we're doing in the space, because it is so, to your point, frontier. It's so extraordinary to be able to blend the lines between, technology and outer space and areas where humans normally don't go. Like, you think about when we did human exploration on the moon, that started in the late 60s, right? At least for the United States. And then, almost 60 odd years later, we're looking at going back to this place and going back to, I know there's some missions that apparently are going to be planned next year for humans to return to the moon. And then you also have this whole technology story with HPE and our, spaceborne computers going up and seeing what the possibilities are in today's era versus like years and years ago when we've done it. Yeah, it's pretty exciting.
I think I'm such a fan of sci-fi, and space. Like, some of my favorite films are films about space, going to the moon, going to Mars. We've heard it on the podcast before, but the story about the gloves is so cool. It's such a clever use of technology. It seems so obvious when you think about it, but it's such a clever use of technology and clever use of the AI tools that we have available to us today.
Yeah. So, Michael, when you were there, and this is for our audience that's listening traditionally through like podcast audio, right? How big was it? Was it like,
right.
What was the size of it? How much did it weigh? Like, what are we talking about in terms of like the overall essence of it?
I think they were the size of a suitcase that you could fit into a cabin hold, that sort of size.
Ah, nice.
They were more than 23 kilograms, I reckon. It took a couple of us to have to sort of lift it onto the table. It's about the same size as maybe a bit slightly bigger than a 4U rack, but just sort of on its side, because it was sort of perpendicular to the way that you'd usually slide it into a rack. So it's quite tall, quite wide, quite deep.
Yeah. So 20 kilograms is about 50 pounds. So it's basically when you check your luggage to go on a flight, that's what the size of it is.
I think it was probably slightly more than that. I didn't get my luggage scales to check. But the Spaceborne Lunar, it was about the size of a graphics card. I could hold it in my hand.
Amazing.
And it was completely gold coloured. It looked like the most blingy graphics card. Mm-hmm. No one's gonna tell me off because it's so much more than that. But it was sort of it was quite cool.
I think it's gonna be really exciting to see like this resurgence of space exploration. I feel like we had a little bit of a lull. Like you think about the space shuttle program and things like that have gone away, and we've kind of had this like gap. But at the same time, building the technology in the back end to now where we're starting to see this come to life. I think it's going to be really exciting, like next 10 years or so, to see what comes to light.
Yeah, I 100% agree with you. Now, Aubrey, throughout the series, we have asked each of our guests why the objects we've discussed are so important to the story of HPE. Mm-hmm. I got one I want to share with you because I think Norm's answer is a brilliant summary for everything we've done and everything we stand for. So just have a listen to this. Why is this object so important to HPE's story?
I think it's important for our future as a company, but it's also a terrific symbol of who we are as a company, our capabilities, our innovation, and our passion to make a difference and do something that hasn't been done before and do it well.
Now, before we finish, we do actually have another bit of news to finish off this episode with. Aubrey, this is going to be your last episode of Technology Now for a little while.
It is. I have some pretty big news to tell everyone. So my spouse and I are expecting. So our baby is due at the end of January, and I will be going on parental leave, which means you probably won't hear from me for a little bit on the show, but we're super excited.
I am really, really excited for you. And
thank you.
Obviously, from the whole team, we wish you the best over the next few months. If you're sort of stuck for names, I've heard Michael and Michelle are really popular right now. Really cool names.
Okay, well, that brings us to the end of Technology Now for this week. Thank you so much to our guest, Norm Follett, and of course to our listeners. Thank you so much for joining us. It's always a pleasure. And if you've enjoyed this episode, please do let us know. Rate and review us wherever you listen to episodes. And if you want to get in contact with us, you can send us an email to technologynow@hpe.com. And don't forget to subscribe, as we always say, so you can listen first every week.
Subject line. What do you reckon, Aubrey? What should the subject line be?
To the moon. Sounds like a good one.
To the moon. Let's go with that. Technology Now is hosted by Aubrey Lovell and myself, Michael Bird, and this episode was produced by Harry Lampert, Izzy Clark, and Spencer Trenwith, with production support from Alicia Kempson-Taylor, Becky Bird, Alyssa Mitri, Rahil Ali Mohammed, and Renee Edwards. Our video editor was Mikey Nissenbaum, and as always, our theme music was composed by Greg Hooper.
Our social editorial team is Rebecca Wissinger, Judy Ann Goldman, and Jacqueline Green, and our social media designers are Alejandra Garcia and Ambar Maldonado.
Technology Now is a Fresh Air production for Hewlett Packard Enterprise, and I'll see you at the same time, the same place next week. Aubrey will be changing nappies, I guess. Cheers.
Goodbye for now.